Hello, good afternoon. Thank you for giving me this opportunity to give a presentation today. My name is Sangyun. I'm working for LG Electronics as a software engineer. I'm in charge of porting, developing embedded software on top of a hypervisor and optimizing the overall performance. This presentation will take about 25 minutes. I'm not a good English speaker, so please allow me to read prepared script for this presentation. If you have any question, there will be time at the end. Let's move to the next slide. There are contents of my presentation. First, you will understand why the virtualization technology is needed in automotive system. Second, let's look at the automotive trend and the current state of GPU virtualization. Third, I'll introduce you a simple real-time GPU scheduler to guarantee real-time rendering for cluster VM on XenGT. Then I'll share the experimental result for performance of many cases. Last, I'll end with my conclusion with what I've learned from my project. First, let's look at the latest trend of digital instrument cluster and in-vehicle infotainment system. Car makers are attempting to integrate two graphics of cluster and IVI into one display, and they are starting to use multiple high-resolution displays, and they are increasing the number of issues and hardware costs due to increasing digital functions. One of the requirements for automotive graphic systems is for the performance of graphic rendering. Cluster applications like speedometer and RPM gauge should steadily run at 6 FPS, and IVI applications like navigation or third-party applications should run at 30 FPS. Then in this slide, I'll explain why the virtualization technology is needed for automotive system. Before explaining, we had exhibited an integrated UI/UX demonstration on a wide display using XenGT at CS show last year. Only special customers related to car industry had been invited for the demonstration. Everyone had satisfied the demonstration of graphic consolidation system. Go back to this slide. I'm going to show you the reason why it is needed. It can support graphic consolidation of separated applications between cluster and IVI system using shared graphics technology. Shared graphics technology consists of GPU virtual. Cluster means the cockpit improved car cockpit cluster. So user can see the speed motor or RPM gauge of. Yeah, right. Yeah. So shared graphic technology is GPU virtualization and graphic layer composition, like this. These two layers are using virtualized GPU, and then compositor integrate two layers to one frame and then display into one display. Each guest OS can use 3D hardware acceleration, and graphic layers are overlaid by software or hardware compositor. It can support high bandwidth for graphic sharing using shared memory. Without virtualization, graphic buffer for IVI layers go to cluster OS through hardware interface, such as Ethernet, it causes tens millisecond delay between IVI application and the display. But with virtualization, IVI and cluster just share the same shared memory, and it has only minor delay overhead. That means it can support high-resolution display for graphic sharing. Also, using virtualization, it can reduce hardware cost about 30% because it shares hardware resource between cluster and IVI system. Normally, GPU driver use round-robin scheduler to handle GPU commands. There is no priority, no preemption for scheduling GPU context. Let's look at the block diagram. It shows simple structure of GPU paravirtualization. Guest OS sends GPU command to front-end driver, and the driver saves them to ring buffer. Front-end driver sends request event to back-end driver to handle them. Back-end driver sends GPU context to the native GPU driver by request other. Native GPU driver submits GPU context to the GPU. Right diagram shows that the red GPU context for real-time rendering can be delayed by scheduling other without priority and period. Red GPU context should wait in a queue and can be submitted after all previous contexts are finished. And there are three types of GPU virtualization solutions. Let's move to the next slide. We divide the GPU virtualization solutions into three types and additional solution for automotive virtualization. First type is traditional backend front-end driver or vOpenGL server client type, like Red Band's virtualized OpenGL solution. It is a paravirtualization type. It is controlled by backend driver. Second type is mediated pass-through type, like Intel XenGT. It is software virtualization type. Guest OS can use modified native GPU driver. The GPU graphic buffer is passed through to the GPU, and MMIO access is trapped and emulated by hypervisor and mediator driver. It is controlled by mediator driver. Third type is hardware-assisted GPU virtualization type, like NVIDIA's GPU. It is hardware-assisted full virtualization. GPU manager driver initializes the GPU to allow guest OS access to the GPU directly. It can use native GPU driver. Each VM, each guest OS control limited GPU resource directly. First type is not a GPU virtualization type, but two guest OS can be passed through to the separated GPU on top of a hypervisor. SoC has two physical GPUs and they are dedicated to VMs. It is controlled by each VM. Moving to the next slide, I say automotive virtualization architecture based on XenGT. Excel tool is modified to set vGPU priority and scheduling period time using Excel configuration file. It creates a guest domain on QEMU with priority and period for vGPU instance. The VGT driver creates a vGPU instance with the values. And then vGPU instances are scheduled based on priority and period. I create two guest domains. I do cluster VM and drive VM. Cluster domain has high priority and 6 millisecond period time, and the IVI domain has low priority and 1 millisecond period by default. High priority vGPU with long period of time gets a chance to use GPU more, I give a long period of time to the high priority vGPU more than low priority GPU due to the characteristic of GPU. GPU is not like CPU. I'll explain it later, slide 9. Let's move to the basic mechanism for real-time GPU scheduling. First, set high and low priority for vGPUs. Second, set different period of time for vGPUs. Third, allow preemption based on high priority of vGPU. If drivers cluster sends first red GPU context which has high priority to VGT driver. VGT driver calls context switch between cluster and IVI, even though third low blue priority context comes earlier than red second context. After finishing second blue context in GPU, first red context is submitted to the GPU. And if there is second red context is in run queue, scheduler doesn't do context switch even though cluster scheduling time is expired. If there is no high GPU context in run queue and the cluster scheduling time is expired, then the scheduler changes run queue from cluster to IVI. In this slide, I'd say about 4 key factors to guarantee real-time graphical rendering for cluster application on cluster VM. Firstly, it should use priority-based preemptive GPU scheduler. Secondly, GPU should support high-speed hardware preemption with fine granularity. Normally, GPU doesn't stop the learning GPU context until it finishes throw call. So high priority GPU context should wait until GPU finishes throw call of the current running GPU context. Let's look at the figure. Cluster apps start to send GPU context to VGT driver every 16.6 milliseconds. If there is running low priority GPU context in GPU, then high priority GPU context should wait until it is finished. The waiting time is T2 time. T2 time is here. T2 time depends on the context of GPU command. XenGT still doesn't support hardware preemption for GPU context switch yet. High priority GPU context should wait T2 time in run queue. Then it should support low GPU context switching overhead between cluster and IVI. In case of XenGT, when the scheduler switches context, there is no need to save and restore context registers. Only current MMIO state registers of vGPU are saved and restored by VGT driver. So T1, T3, and T4 time of context switching overhead are lower than T2 time. Lastly, graphic applications should be designed using lightweight GPU context. If graphic application use heavyweight GPU commands, T2 time will be increasing. It makes the scheduler hard to schedule for real time. T2 time is the most important key factor for real-time scheduling. Let's move to the experimental result. I used Intel NUC board which has i5 4 cores and 8th generation named Broadwell GPU. Looking at the bar graph, it shows the result of GL Mark II ES2. Blue bar shows the GPU performance without period. Red bar is with high priority and 6 milliseconds for DOM-1 and low priority and 1 millisecond period for DOM-2. With a priority and period, it shows almost the same result due to the round-robin scheduler. But with the priority and period, DOM-1 is 3 times higher than DOM-2. In this slide, let's look at the result when I run a Qt cluster application on DOM-1 like this. And the GL-Mark2 ES2 benchmark on DOM-2 at the same time. Blue line of 2 graphs shows the result when the cluster application and GL-Mark2 ES2 run without priority and period. Red line of 2 graphs shows the result with priority and period. The result of upper blue graph didn't meet the 60 FPS most time, but with priority and period, the result of upper red graph meet 60 FPS overall. As you can see the black box, there has been lower performance than the others. The terrain test case of GL-Mark2 use heavy GPU context and memory, so high priority GPU context could not run on time. High priority contexts are delayed using until finishing a GPU context of terrain. I've tested to see what if domains have different number of vGPUs and GPU affinity. How these test cases affect the GPU performance. In case of case 1, case 2, case 3, and case 6, GPUs were scheduled by credit scheduler. These test cases met real-time rendering for cluster application, but the performance of GL-Mark2 for DOM-2 were not good. Context switching overhead for GPU might affect the execution time for DOM-2. When domains use dedicated and separated CPUs, vGPUs, the performance results were better than vGPUs were scheduled. Especially the result of case 8 was the best. I did another test to find out the best case with different period and priority. I set high or low priority and changed scheduling period looking at the case 3. DOM-1 is low priority and 6 millisecond period. It shows that the period is important QoS for real-time rendering. Let's look at the case 4. DOM-U is high priority and 1 millisecond period. It shows that the result of DOM-2 is higher than case 1 unexpectedly. So, well, it needs more investigation. I don't know why yet. Like case 6, cluster app meets 60 FPS real-time rendering, and the performance of DOM-2 is higher than the others. In case 9, if I increase the period time up to 9 milliseconds, it can guarantee the real-time rendering for cluster application, but the performance of DOM-2 was decreased. Summarizing what I have been presenting, Automotive Virtualization Solutions will be included in next car generation. We are preparing Automotive Virtualization Solutions and providing our solutions to customers. There is still nothing for Automotive Virtualization Solution, but I believe that the journey is already starting today. And I hope GEM project will be one of Automotive Virtualization Solution in the future. Before I conclude my presentation, I want to give you some tips if you are considering or starting an automotive virtualization project. You should consider it from the beginning of hardware system design. Select a proper process with hardware assist virtualization within limited cost. Design hardware partitions for CPUs, memory, and I/O. If a SoC have enough cores, I recommend you isolate cores for domains for the safety and performance. Design robust hardware and software system for safety. Automotive's embedded systems should meet the safety requirements such as ISO 26262. And finally, when you develop a GPU virtualization to consolidate cluster system and IVI system, you should consider the real-time GPU scheduling for cluster VM. Firstly, GPU should support hardware priority and preemption features. Secondly, graphic applications should be designed with lightweight GPU context. Lastly, hardware-assisted GPU virtualization is needed to reduce software overhead and risk for safety. Thank you for listening. That concludes my presentation. I'll show you a short demo video in next slide. Test of frame per second. First application cannot meet 60 FPS. With priority and priority meet 60 FPS. And almost up to 60 FPS. Thank you for listening. Comments. Yeah. XenGT, use basically use round robin scheduler, but I modify it, use priority different priority time. Yeah, fixed priority preemptive scheduling. Yeah. Yeah. Yeah, right. Yeah, right. Yeah, right. Well, I ask for my project leader before I open it. Maybe there is another Qt application. I tell you the another Qt application for cluster example.